All right, let's get started. Okay, PS5 is due this week. PS6 will come out the end of the week, and then the following, so let's see, we do PS6 next week, and the week after that is the midterm. So the midterm is February 27th. And the midterm will cover through this week. Plus, I think a little bit will spill over into next week, one topic. But that's where we stand. I'll have more to say about the midterm later. Any questions about the assignment or about anything else? Okay. I want to say one thing about the caddis problem. It has potential to be very easy. You got to do two things: a breadth first search, and then you need to sort the vertices based on the outcome of the breadth first search. Where people make it hard is they try to do the sorting while they're doing the breadth first search. So don't do that. Do the breadth first search and then sort afterwards based on the information you derive from the breadth first search. I've seen all kinds of convoluted solutions that, I mean, they can work. It's just harder if you don't do it that way. All right. Last time we started talking about strongly connected components, and we will resume that here. And we already did some of this. I just want to remind you what strongly connected components are. The idea is you have a directed graph, and connected components are subsets of the vertices such that you can get to any vertex in the subset from any other vertex. And strongly connected components are sort of maximal size such components. So this graph here is divided into 5 strongly connected components, indicated by the dotted lines. The property is that inside the dotted lines, every vertex can be reached from every other vertex. And furthermore, there's no way to make any of the dotted areas bigger. They're as big as they can get. So this graph decomposes into 5 strongly connected components. We also, some terminology. After you've identified the strongly connected components, if you ignore the internal structure, so I got rid of all the arrows, the edges, and the vertices inside those strongly connected components, and then I get rid of duplicate edges between components, like there's 2 from BE to CF, so I get rid of one of those. What remains is a DAG. So you can, strongly connected components algorithm is a way of abstracting away from the structure of a directed graph and viewing the thing as a DAG. Why is that interesting? Why is it useful to be able to do that abstraction? I mean, we've lost a lot of information about the graph when we convert it here. Yeah?
Well, now we can topologically sort this where we couldn't do that to the original graph.
Okay, so he's saying we can topologically sort this, or more generally, we can apply DAG algorithms to that. And DAG algorithms are usually pretty efficient. And so we looked at least one problem where to solve it, it's a problem on a directed graph, but to solve it, what we can do is you reduce it to a DAG like this, to the metagraph, solve a related problem on the metagraph using a DAG algorithm, and then convert that solution to a solution on the overall DAG. So that's often an easier way to solve a problem. So that's what we spent time on last time, was seeing how that works. DAG to metagraph, solve a problem on the metagraph, and then enlarge that solution to a solution on the original graph. So this is some of the stuff we talked about, so I'll skip through that. This is what we observed at the end, toward the end. If we were smart enough, so we're trying to find a way to identify strongly connected components. So if we somehow had some way to identify a a vertex that happens to be in a sink of the metagraph, we could identify that entire sink. And to show you what I mean, suppose little bird told us that G happens to be in a sink metavertex of the metagraph of this thing. Now we don't know what the metagraph is, because that's what we're trying to discover. But suppose we just happen to know that G was in it. Well, then all we have to do is explore from G, and it will visit everything. We know that those 6 vertices form a sink in the metagraph, and we've picked them all off. We have identified, we have visited just the things in that sink. Now, why did that work? Why did starting in the metasync and exploring let us identify everything in it?
Because since the sink, I guess in the metagraph, is a countable object to explore everything, but since it, and again, in the meta object, there's nothing more than the sink.
Okay, there's no way out of there. So we know they're all connected, so we're going to visit them all. Furthermore, there's no way out, so that's all we're going to visit. So that's the basis of the algorithm. We're going to find a vertex that we know is in the sink of the metagraph, and then find that metavertex with explore. But that leaves 2 questions. Once we've done that, well, first of all, the first question is, how do we find that vertex is in a metasync? And second of all, okay, after we figured out that those 6 vertices are in the metasync, how do we get the rest of the vertices in the metagraph? How do we continue from there? Now let's leave the first question behind for a second. The second question, what could we do? Once you've identified that sink, how could we make progress, identify some other metavertices? Yeah.
Remove it from the graph, and now there should be a new thing.
Right. What if we removed it from the graph, either physically or everything's visited, so it's sort of it's gone already? What would be left if we took out G, H, I, J, K, and L? What would be? Suppose now someone told us, oh, in this new graph, I can tell you a vertex is in a metasync. What might they tell us? What's an example of a vertex that's in a metasync of the reduced graph? Once we get rid of that thing we've already marked up. Yeah? D. In fact, D was a sink in the original metagraph. So, okay, we'll do an explorer starting at D, and it'll visit D and stop. We've identified another metavertex. Throw it out. Okay? Now, there's one metasync, CF. If someone tells us F, we do a search starting there. That will identify CF. And then someone tells us B, and we'll find B and E, and then finally we'll find A. So if we had someone to tell us where to restart each time, we could tick off the metavertices. Now, in what order are we moving through the metagraph when we do that? Identifying the sinks first. Yeah?
Reverse topological order.
Reverse topological order. Remember, the metagraph is a DAG. We're basically moving. We start with, we're either going to find the six vertex thing first, or the 1 vertex D, and we work back toward A. So you'll see all these things come into play. But the question, though, is, how are we going to find a vertex that's in a metasync? Either of the original graph or of what's left of the graph. So let's see what we can do about that. What I observed, what I'm going to do is just go ahead and do a depth first search. Starting at C, and then when I get stuck, I'll go to D and then A, just for the heck of it. So this is just sort of an arbitrary depth first search. And we do that. Now, I want you to look at just the post times. And what this property over here is saying is, if you have a vertex, imagine you had a vertex like, you have a metavertex. So take that metavertex CF up there, and take that metavertex GH so on down at the bottom. So we got these 2 metavertices. So you pick any 2 metavertices, this one here and this one here, for example. In the metagraph, this vertex would come before this vertex because this is the sink. Okay? What's the highest post time up here in this vertex? 16 is the highest vertex here. And what's the highest vertex down here? 14. So this property over here is saying that the highest vertex up here, the highest post time up here in this chunk, will be larger than the highest post time down here. And that applies for any pair of vertices in the metagraph as long as, there's a path from one to the other. So let's try it out. What about this one here and this thing down here? Highest one up here is 23. That's bigger than the 14. Now these two, this one and this one, the highest one's 23, the highest one is 16. Okay, over here, 23, 18. It always works out. So where will the highest post time be? For this graph in particular, it's up in A. But what can we count on in general? What's the most general answer you could give? You do a depth first search.
You can get anywhere from there?
Not necessarily. It's not true you can get anywhere from there. It is for this graph. Where will that highest vertex be? Yeah.
In the meta source?
In a meta source, yes. The problem might be there are a couple, you could have a metagraph with two meta sources and you can't get from one to the other. But the highest post time will be in one of the meta sources. Okay? But that's the opposite of what we need. Right? It'd be nice if the property were the smallest post time is in a meta sink. Then we'd be in business for our DAG for our SCC algorithm. But we're not identifying a sink this way. We're identifying a source. It's kind of backwards from what we want. Now, people are always wanting to propose that, well, maybe the smallest post time is in a sink. Well, does it work out here? What's the smallest post time?
9.
Okay, 9. The smallest post time is in this sink. That's good. Let's see if it keeps working. Is the smallest post time here smaller than the smallest post time there?
Yeah.
Yeah. Does it hold for this pair?
Yeah.
Yeah. Okay. Does it work?
In this specific example.
In this example, see if you can come up with a graph. I can think of one with 3 vertices that foils this property, where the smallest post time isn't in a meta sink. It's actually in a meta source. I'll spot you 3 vertices. So here we go. A, B, C. So what edges can I put in so that I can do a depth first search and end up with the smallest post time in the meta source instead of the meta sink? Yeah.
Edges from A to B, B to A, and then from B to C.
Okay. So like that?
Yeah.
Okay. So let's do a depth first search. Now depth first search can start anywhere. So if we start at A, what are we going to get? We're going to get a 1, and then we'll go down to B, that's 2. We'll go down to C, that's 3. It'll go at a post time of 4. B will get a post time of 5 and a 6. And the smallest post time is in a meta sink. Remember that's the meta sink right there, and the other thing's a meta source. Okay? But it's not a bad example. What do I have to do to demonstrate that it's not a bad example?
Change which one's the source.
Just start in a different place.
I can start in a different place. What if I start the depth first search at B? Because you can start it anywhere. We don't know. Suppose I started at B and it got a time of 1, and then I next visited A. It would get a pre-time of 2, and then what happens?
3.
We're done with A, nowhere new to go from A, so it gets the 3. We would back down to the B and then go down to C. It would get the 4, the 5, and we get the 6 right here. So the smallest post time is right there in a source, in a meta source. Now, just to check, in both cases, where was the largest post time?
Still in the source.
In this case, it was A, and in this case over here, it was B, but both of them are in the meta source. So that's more evidence that my assertion is true. We can identify the meta source, a vertex in the meta source. We can't identify, at least I don't know a way to identify directly a vertex in a meta sink, just by doing a depth first search. All right, any questions about that? Okay. So what do we do? We're not getting what we need. Yeah.
Do we just reverse the graph?
That's it. What if we reverse the graph and did this procedure? So if we reverse the graph and do the depth first search, yeah, we're going to find that the highest post time is in a meta source. But that meta source corresponds to what in the original graph? It's a meta sink. So let me show you how that works. And we just looked at that. So this is showing you from the other point of view. Suppose we could identify meta sources. So we know that A has the highest post time, so it is in a meta source. Now suppose we could identify the rest of the vertices in the meta source, which we don't know how to do. We only know how to identify vertices in the meta sink. But if we could somehow do that, we could get rid of that. What's the biggest left in this one? At 23. So let's get rid of that chunk. What's the biggest one next? 18. So that's a chunk. We'll get rid of, then 15 is the biggest, and then that. So that's sort of our algorithm in reverse. We're going to do a similar thing, but working backwards. So here's what we do. So here's the graph we're working with. Let's reverse it. I just flip all the arrows around. Then do the depth first search. Okay. Then we're going to sort the vertices in reverse order of post time. So I'm just going to pull them out down here. Okay, so let's see. J comes first. So it had the highest post time. That means J is in a meta source of this reversed graph. Is that correct? Sure. That chunk at the bottom of 6, that originally was a meta sink, but now in the reverse graph it's a meta source. And that A comes last, because it was a meta source originally, now it's a meta sink. So we reverse the graph and do the sort just to get this ordering. Then we're done with the reverse graph. The whole purpose of reversing the graph is just to get this ordering. Then you go back to the original graph, and we start exploring. But we don't pick where we start arbitrarily. We start with J and do an explore. And every time we visit a vertex that's on this list, we'll throw it away. So let's do that. We'll go to J. We've been to J. I've removed it from the list. We go to I, it comes off the list. Then G comes off, H comes off, K comes off, L comes off. And done. So we have identified a strongly connected component. Now the cool thing about this is, what's left of this ordering tells us where to restart, do the next explore. It says, okay, now pick up with D. We're guaranteed, after we've gotten rid of all those yellow vertices, that the first vertex will be in a meta sink of what's left. So we go to D, and we've identified that strongly connected component. Now, it says to restart at C. So we go to C, and we're done with that. Then it says start at B. We identify that, and then it tells us A. And we pick them all off like that. So it's as simple as that, 2 depth first searches. The first one on the reversed graph. So I guess you have to reverse the graph, do a depth first search on it, and then do a depth first search on the original graph, using the results of the first depth first search to control the second depth first search. And that's a strongly connected component algorithm. So, what else to say? That's the algorithm. What's the complexity? Yeah, it's linear, in the sense, the sense of linear we've been using, which is that it takes time proportional to the size of the graph representation. Because it's just reversing can be done in linear time, and so can the two depth first searches. So that's that. Okay. Any questions about that? Okay, now, this topic, breadth-first search trees, actually starts a new chapter in the book. So we've been studying depth-first search, basically. And with depth-first search, we were doing depth-first searches in the end, and most of the time, to get those pre- and post numbers. So depth-first search, the actual title of the book is Graph Decomposition, taking the graph apart to find out information about it using depth-first search. The title of the next chapter, chapter 4, is Graph Search. So when you're trying to find a good route from here to there, you don't do depth-first search typically, because you use a breadth-first search or some other similar sort of thing. Why? Why is depth-first search not really the right way to find out a path? Yeah.
So because it won't necessarily find the quickest path?
Right, it's not going to find a path in a particular property. It could be a long path. And you'll notice that when we did depth-first search, we didn't ever record any paths. Sometimes in my animations, I would color vertices and you could see the depth-first search tree, but we really didn't try to preserve that. Only thing we really preserved were the pre and post numbers. With breadth-first search, it's different. Breadth-first search, the result of the search is a tree that tells you the shortest path between pairs of vertices. So let me show you what I mean. So breadth-first search begins at a specified vertex and finds the shortest path to every other vertex. Now that's different from depth-first search in a couple ways. One is the shortest path, but the other one is, with depth-first search, there was no definition of where you start. It didn't matter where you started. You started somewhere, and when you've explored all you could, you restarted somewhere else. With breadth-first search, a parameter to breadth-first search is the starting vertex. And after you finish doing the breadth-first search at that vertex, if there are some you didn't reach, you just don't reach them. You don't restart the breadth-first search and do another search. So I'm going to highlight some paths. So suppose I want to find the shortest paths from A to every other vertex. So look at the upper right graph. I'm going to highlight the shortest paths. So that's the shortest path from A to B. Okay? Shortest path from A to C. So I've colored one yellow, one red. What about the shortest path from A to D? What is it? Right, either A to B to D, 2 edges, or A to C to D, 2 edges. They're both equally good, so I'll just say that. And then finally, A to E. That's going to be, again, there are 2 paths, A, B, D, E, or A, C, D, E. Let's say I pick that one. Equally good. So in that graph, the shortest paths between A and every other vertex are highlighted with different colors. But there's a problem with the way I did it. They don't form a tree. So if we sort of ignore the colors and just notice which, just let me see if I don't have a, imagine that we change them all to the same color. You don't have a tree. What do I mean by that? You don't have it, that doesn't form a tree. The edges that we're using, we don't use the edge from B to C, the rest of the edge we use. So in what sense does it not form a tree? Yeah?
Both the B connects to D and C connects to D, so they're sharing the same
Right.
node.
D has 2 parents, basically, and that can't happen in a tree. However, it is always possible to do a breadth-first search to find shortest paths that do form a tree. I don't know what happened to my edge from B to D there. It'll come back in a second. So those are, up at this point, our edges form a tree, right? A is the root, and then A has two children, B and C, and then D has, B has a child D. Only, you don't have multiple parents. Now, before we put in the path A, C, D, E, and that sort of compromised the tree structure, but what could I have done to maintain a tree structure? A, B, D, E. If I'd only chosen that, then I would have so there's, the top one is the A, B, D, E edge, and then if we just replace all the colored edges with one purple edge, you can see it's a tree. So the algorithm we're going to look at will always produce a tree, a breadth-first search tree. And we'll take advantage of the fact that it forms a tree. It makes it easier to store all the paths. Okay? And here's how we do it. The output of our breadth-first search tree will be two arrays, or two lists, however, previous and distance, indexed by vertex name. Of course, in a program, these might be maps, not arrays. Previous tells you what the tree is. So for every vertex, you're told the parent. So A doesn't have a parent, so it says null. The parents of B and C are both A. You can see in that purple tree there. The parent of D is B, and the parent of B is D. So this, you can reconstruct that tree right there with the orange, or with the purple from this. This gives you the tree, and this gives you the distance from A to every vertex. So the distance from A to itself is 0, the distance from A to B to itself is, from A to B is 1, and so on. Where distance is measured, the number of edges traversed. When we add 8 weights to the edges, we won't be dealing with breadth-first search anymore. We'll do a shortest path algorithm, but for now there are no weights. Now, distance is redundant. How could we, if all you had was the previous array, how could you reconstruct the distance array? Right? Like, how could you decide that, if these were all blank, how could you decide that E needed a 3 next to it? Just using the previous array. Yeah?
Well, since you have like the previous node D, you just find its distance, like D is the previous node D, you find the distance of D, and you kind of go back up.
Yeah.
So I get to A.
So this says E's parent is D, that's 1. D's parent is B, that's 2. B's parent is A, that's 3. A is the root, so 3. So we could dispense with distance. It turns out you need this information as you're doing the algorithm, and it's useful to have it later, so we'll just keep it around. Kind of a pain to reconstruct it every time you need it. Okay, so there we have, we want this kind of output for breadth-first search. Now that caddis problem I mentioned, when I said you do the breadth-first search and then you sort, this is the information, this is at least some of the information that you need to do the sort at the end. You need to know these values here. You also need to know the names of the vertices, because they matter as well. So the sort you want to do in the end is a combination of sorting by distance and sorting by vertex name. Fortunately, you can create custom comparisons in languages to sort any way you want. Now, what would happen if we had a vertex that could not be reached? Like F right there. You cannot get to F from A.
Previous is null and distance is infinite.
Right, so we'll do previous null, and we'll have some, we just have to have some value to indicate F is an infinite distance from A.
I guess you could do like -1. Instead of negative distance.
Yeah, you can, yeah, -1 will work for infinite. So there are various tricks. So anyway, that's how we can do it. So here's the algorithm. I imagine you've seen breadth-first search algorithms before. But this is the pseudocode for what we'll be using. So let's look at how it works. First thing we do is initialize the distance in previous arrays. So we're going to set the distance of everything. We're going to store infinities all through the distance array, and we're going to store nulls all through the previous array. So we execute that code. This is what happens. Now, we also set distance of s, which is the start vertex, which is a parameter you can see, to 0. So that's our starting situation. We know that the distance of A to itself is 0, and then we don't know anything else. Now, we also use a queue, and that's abbreviated here. A queue data structure is going to play prominently in this algorithm. So what we do is we create the new queue, and we enqueue S. So our start vertex is A, so we're going to throw it on the queue. So that sets things off. Now I'm going to use colors over there and down here as the algorithm goes along. So purple means that the vertex is currently on the queue. White means we haven't encountered the vertex yet. So we're going to search starting with A and work our way out through the graph. Vertices will be white until they're first spotted. Okay? And then we're going to use, I believe, yellow, meaning a vertex has been on the queue and has come off. So let's watch this in action. So we've got this loop here that says while the queue is not empty, we always take the first element off the queue. So we take it off, so it'll disappear from the queue, and we're going to color it yellow just so we remember, that's been on the queue and now it's come off. This is just reflecting the animation, not in anything else. And now what you do is you look at all the white vertices that you can reach from A. Now how can you tell? There's no colors over here. So how can we tell some vertex is white? In other words, hasn't been seen before.
Its distance is infinity.
Right, its distance will be infinity. So you look at your neighbors whose distances are set to infinity, meaning we haven't encountered them before, and we immediately can add them to the tree and to the queue. So what we do is three things. We add it to the queue, so it'll show up here on the queue. We set the previous of that vertex. So V is the vertex we just discovered, where, remember, U is where we are right now. We're looking for an edge from U to V, any edge of the form U to V. So V is where we're going. So V in this case is going to loop through E, F, and B. And so what's this saying here? When we set previous of V to U, what are we doing? What will previous of B and E and F be set to? A. To A. Right, so that's what that does. And then that says make the distance to this new vertex one more than the distance from U. Okay? So let's see how that works. So the first thing that happens is we try to go to B. It has a distance of infinity, so we throw it on the queue. And notice also I set previous of B to be A and the distance to B to be 1, which is one more than the distance to A. All right, that's that. Now we try E, and what's going to happen?
Same thing. Throw it on the queue.
Same thing. It'll go on the queue, and then focus on row E on those two arrays, and you'll see they will change to A and 1. And then same thing with F. So what we've done at this point is we found the shortest path from A to B, E, and F. As soon as the distance turns to non-infinity, or the previous turns to not null, we know that we have nailed down where this thing is, what the shortest path is. And the path is recorded in the previous array, and the distance is recorded in the distance array. Okay? Now there's nothing more to dequeue. I mean, there's no more neighbors of A, so what happens next?
There's the next thing in the queue.
We just go back to the queue is not empty, so we pull B off and repeat. Well, let's see what B does. B looks at C. What's going to happen?
Throw C on the
C goes on the queue, and then look at the row for C. It'll change to B and 2. So it's B this time because now U, the value of U is B this time. And we stored a 2 in distance because that's one more than B's value was. Okay? Then we're going to look at F and what's going to happen.
Nothing.
Yeah,
It's not-
F is purple, meaning, or more to the point, F is not infinite. So we ignore it, because we just found a longer path to F. We don't care about longer paths. So we're done with B, so we pull E off and repeat. E tries to go to F, that doesn't pan out. Nowhere else to go, so we pull F off. F tries to go to C, that's no good, and that's a dead end. So now we pull C off, it tries to go to D, that's something new. So D will update, and we try to go to G, that's new, and so G will update. Then we pull D off, it tries to go to H, that works out. Then we take, I just pulled G off, and nowhere for it to go. And H comes off, and nowhere for it to go either. So we're done. Notice we never reached I, so it stayed infinite. So that's breadth first search. What's the fundamental difference between breadth first search and depth first search? They seem very different because depth first search is recursive, breadth first search is iterative. Breadth first search uses a queue, depth first search doesn't. They both have loops sort of like this. They're looking for all edges and doing things to them. Yeah?
Breadth first search finds the shortest path.
Breadth first search finds the shortest path. Depth first search makes no such guarantee. Yeah?
Breadth first search goes to every child of the thing first rather than going all the way down.
Okay, so breadth first search, depth first search will find a child and then use spend its attention on that child before backing up and trying any other children. Breadth first search sort of is breadth first. What makes it work? What causes that effect in breadth first search? Yeah, the queue. It's the queue. Things enter at the back and exit at the front. So we're always exploring from the things that have been on the queue the shortest, the longest amount of time. So breadth first search uses a queue to control which vertices are searched next. What does depth first search use? Yeah,
It's a stack.
a stack. Depth first search uses a stack. Now you're thinking, what's stacked? There was no, the depth first search code, you did not see code that says S equals new stack. So where do we get off saying depth first search uses a stack? Yeah, in the recursion, it uses the runtime stack of the programming language. Now, you can write an iterative version of depth first search. And it ends up looking pretty similar to breadth first search. What would be the trick to writing a non-recursive version of depth first search?
Building a stack.
Yeah, you would have to explicitly manage your own stack. So you would have a stack of vertices, like breadth first search has a queue of vertices. But you've got to be careful. Sometimes I assign this as a problem. I'm not this year. Because it's, the pre and the post numbers, unless you're careful, when you write your iterative version, you're going to get the post numbers wrong. Okay? Because when does a vertex get its post number in depth first search? Yeah.
When it has no children left to go to.
When there's no children left to go to and the recursive call returns. Right before the recursive call returns, it's given a post number. But if you use a straightforward iterative stack implementation, you won't be able to recognize when the recursive call is returning because there isn't a recursive call to return from. So it turns out you have to push extra information on the stack to say, okay, when this is popped, assign the post number. I don't mean to dwell on this. I just want to point out that they're not as different as you might think. Essentially, searching with a queue gives you breadth first search. Searching with a stack gives you depth first search. But since you get the runtime stack for free, we just exploited that. Yeah.
Performance-wise, how much is the difference in performance whether you do it iteratively or recursively?
Well, okay, so if we're comparing the iterative version of depth first search to the recursive version, okay, let's measure it different ways. What about stack depth? The problem with recursion is if you're unlucky, your stack can get really deep. Like imagine if your graph had 1 million vertices and they were linked in a single chain. What would happen with depth first search? You end up with 1 million stack frames pushed at some point, and that'd probably exhaust the stack. But if you're doing it iteratively, the stack can also get 1 million elements deep. You know, your private stack. But what's the difference between your stack of vertices versus the programming language's stack of stack frames? Yeah.
Programming languages stack frames take up more memory.
Yeah, a stack frame's a lot bigger than a single vertex. So that's one thing. It takes more memory. The recursive version is going to take more memory. Furthermore, most languages put a limit on how much space you can go to the stack. If you do your own personal stack, that's going on. You know, the stack is stored on the heap, and heaps are generally much bigger. In terms of time, it's not so clear cut. Each recursion is an extra method call, but that's a little bit, but it's not. If that were the only difference, it wouldn't be worth worrying about. The main thing is the space. Okay, let's analyze breadth first search, and this is so similar to the analysis of depth first search, it ought to look pretty familiar. So remember, we got V vertices and E edges. What happens, that first block of code, that initialization code, that for each loop down to distance of s equals 0. What's the complexity of that? Basically initializing two arrays. Yep, O of V. Each array is of length V. So it's going to be proportional to the size of V. So that's O of V. What about creating an empty queue? That's constant. What about pushing or queuing an element, adding to the back of the queue? That's constant. Okay, that loop test is constant, but how many times do we do it? At most. Yeah, V times, once for each vertex. Basically, that loop is going to iterate once per vertex at most, because you can only come off the queue once before the queue becomes empty. So that's O of V. V times we do a constant time. Okay? What about this DQ step right here? That'll execute at most V times. Each one is constant. So that's another O of V operation over the entire life of the algorithm. Then, we've got to find all the edges. We made this argument before. Sometimes through this outer loop, we're going to find a few edges. Sometimes we're going to find a lot. But over the course of all the iterations of the outer loop, we're going to have to look at every corner of whatever data structure we're using to find all the edges. So that depends on how we're going to represent it. So I'll punt and just say that's just whatever the cost of enumerating the edges is for whatever representation we use. Okay? Then we got this test. How many times will we do that test over the life of the entire outer loop? How many times will we test a distance of V to see if it's infinite? Yeah, once per edge. Because what this does is generates all the edges out of U to some vertex. And it does it for every possible U. So essentially, this loop runs once per edge. I mean, this loop, over the life of the entire algorithm, in the life of the entire outer loop, we're going to identify all the edges. That's E. Then what about these things down here? These are 3 constant time operations. How many times are they executed? Not E. How many times can a vertex go over with you? Just once. So the idea is, the first time when we look at an edge into a vertex, we enqueue the vertex and we set the distance to non-infinite, and we set that to non-null. That means the next time we find an edge into that vertex, we're going to ignore it. So this can only be true at most V times. All right, so we got that. We got that. We add them all up, we get this. O of V plus O of E plus whatever the cost of enumerating the edges are. For a matrix, the cost of finding all the edges is O of V squared. That dominates the others, so we just have O of V squared. For the list, we get that, and that simplifies to that. So again, it's linear. Same result we got for depth first search. Okay, so that's all I have to say about breadth first search. You'll need to implement it, of course, for the caddis problem, and then there's another problem, a simple one, that asks about it. But any questions I could answer here?
What is the body of conditional O of B?
This here?
Yeah, yes.
Okay, he's asking, why is the body of conditional O of V? Okay, so first thing to realize is, when I say body, one execution of the body of the conditional is constant time. But the body is executed V times over the entire life of the algorithm, once per vertex. So V times constant equals to V. Yeah, I guess I should say body conditional over life of algorithm. Test and loop over life of algorithm. Okay, any other questions? I'm sure this really is the last one. Okay, so let's take a break and we'll talk about shortest paths. All right, now we're going to change the problem slightly and introduce weights on the edges. So now before, breadth first search was, the definition of the shortest path had to do with number of edges. Here, though, it's going to have to do, we've got to add up the weights on the paths to identify the shortest ones. So essentially, breadth first search is a special case of this where all the edges have weight 1. So now we're not going to have, we're going to have different weights. we're going to make an assumption. We're going to assume that there are no cycles in the graph of net negative cost. Now, what the heck does that mean? What is a cycle of net negative cost? Yes?
I would presume it's a situation where if you keep looping around, you subtract from your overall cost.
Okay, so it's a cycle where the weight to go around the cycle is negative. So this graph has a cycle. That cycle F, C, G, F is a cycle. But that's not a cycle of negative cost. It's a cycle of cost 1. So that graph is okay. So here is the shortest path. I've colored the edges yellow that make up that encode the shortest path tree. So this is just like the breadth first search tree. The shortest paths encode to a tree, can encode to a tree. So what is the shortest path from A to E? You can find it just by working backwards from E. Just follow the edges backwards out of E. Yeah. Yeah, A, B, C, G, F, E. And what's its weight? Let's see, 2, 3, 4, 5, and then the negative 5 gives us 0, 1. It's path of length 1, if I add it right. Now you see breadth first search wouldn't get the right answer here, not surprisingly. And there's the answer encoded in the same previous and distance arrays as before. So it's working just like breadth first search. In fact, we'll see the algorithms are all that different from breadth first search. All right, so that sort of sets up the problem. Now, what's the problem with a negative cycle? So I changed that negative 5 to a negative 7. Now the cycle has a net negative cost of 1. Yeah?
You would have like an infinitely short distance because you could always go back around again.
Okay. So he said you have an infinitely short distance. Essentially, no finite path could be the right answer. I mean, what's the shortest path from A to C in this case? Well, you could say it's A, B, C of weight 3, but could you come up with a shorter path? Yeah, A, B, C, G, F, C of weight 2. Well, is that the shortest path? Go around twice, and you have weight 1. Go around 3 times, you weight 0. You can go around as many times as you want and make the path as short as you want, but that's not the answer. There's always a shorter path. So really, the problem is ill-defined here. There's no solution. So we end up with sort of that situation. So that's why we rule those out. Now, you could think of a different question. Instead of asking for the shortest path, what if we ask for the shortest path that does not include a cycle? So now this is that. This is the shortest path where none of the paths involve cycles. So you can see the shortest path to E and F are both negative because we can use that negative 7 edge once. But we can't use it multiple times. So that's sort of the general shortest path problem. To find the shortest path where you're not allowed to use cycles. Unfortunately, this particular problem is no one has ever found an efficient solution for it. It's NP complete. We'll discuss that at the end of the semester. But bottom line is it means it's extremely unlikely that there's an efficient algorithm to solve this general shortest path problem. So we end up looking at special cases. We'll look at 3 different special cases. So you could become extremely famous if you solve the general problem. All right, that's the end of that. Now this is a PowerPoint slide, so just be aware of that. I've never converted this one to Google Slides. So this is back the slide we were with on the previous slide deck. Now, I mentioned we're going to look at 3 different algorithms for shortest paths. But all 3 algorithms use the same fundamental operation called the update operation. And all these algorithms operate by doing update operations all around the graph, and they differ in the order in which they do them. That's the only difference, and they differ in how they decide on that order. And so this is the update operation. You run update on an edge. So to update the edge from U to V that has weight W, what you do is you look at your distance array and you see, is the distance to V that's currently recorded in the distance array. So imagine the distance array and the previous array are going to have the shortest known paths to each vertex, just like breadth first search did. Initially, there will be no paths known, and we're done, perfect paths will be known. But at any time in the middle, you're going to have your current best guess. So if the distance to V is greater than the distance to U plus W, we do something. Now, what does it mean that the distance of V that we know about is greater than the distance of U plus W? What have we discovered when we find a situation where the distance to V recorded in the data structure is greater than that sum?
A shorter path.
We found a better way. So currently, we know a way to get to V that's some amount. However, if we, this is saying that if we go to U, and that's distance of U away, and add the W, which is the cost of the edge from U to V, we have found a shorter way to get to V. It's saying that you can go from the root to U and then to V via this edge. That's shorter than whatever way we previously discovered. So if it is, we need to record that fact. And all we do is we record the fact that, okay, the previous of V is now U, and its distance of V is this new distance we discovered. That's the update operation. And here's the cool thing about the update operation. You can start with the distance array and the previous array like we did for breadth first search, where it's full of nulls and infinities, except for the 0 at the start. And you can just start blindly updating. You can pick an edge at random and update it. Pick an edge at random and update it. And keep doing that. Some of the updates will have no effect because that condition won't be true. Some of them will improve the graph. And if you do this the longer you do it, you'll never make the graph, never make the answer less good. You can only get closer to the ultimate solution. I can't guarantee you'll get to a solution if you're picking the edges at random. But there's no harm in applying the update operation at random other than wasted time. You're not going to get into a dead-end situation. So the whole trick in these algorithms is just to decide in what order to do the update. So let's try out update right here. So what will happen when we run update on AF4, on the edge from A to 4, which has weight, on the edge from A to F, which has weight 4? What will change about the previous and distance array? So this is the initial state. Okay, so keep in mind, F is playing the role of V, and A is the role of U, and 4 is W. What's the current distance to V, the distance to F? Just look in the distance array. Infinite. Okay. Is that greater than the current distance to U? Remember, U is A, so what's the distance to U? Distance to A. That's 0, and then plus the 4. So is infinity greater than 4? Yeah. So we're gonna change the distance array in the previous array to what? What will change in the distance array? What will be stored next to F? 4, and what's the previous going to be? A. Boom. So we found a shorter way than infinity. That doesn't mean it's the shortest way. It's just a better way. And the idea is sometimes we'll apply this update operation, nothing will change. Sometimes we apply it and it will change, but it always changes for the better. Never goes backwards, never gets you stuck. What about that one right there? What if we try to update the edge from C to G of weight 2? Okay. Previous becomes C, distance becomes 2. Well, let's try it out.
I was just
No,
gonna
never
say-
mind.
You retract your answer.
Yes.
Okay. So explain why you retract it.
Oh, because I just noticed C has distance of infinity on right there.
Right. So the thing to realize is when we do distance of V, so V is G, that's infinity. But what's distance to C? Distance of U. It's infinity. And it doesn't matter what you add to infinity, you still got infinity. So infinity is not greater than infinity, so we don't do anything. So that's an example of an update that has no effect. So that tells you one thing. If you're going to do an update, don't bother if the known distance to U is infinite. There's no point. You need to do the update start, and initially the only thing you know anything about is A. So you want to start at the start and work out, which makes sense. Just updating in the middle doesn't help. That doesn't have any effect. What about FE1? So we know the current distance to E is infinite, and the distance to F is 4. So yeah, that update's going to work, and what's going to change? Yeah?
The distance to U will become 5, correct? Or-
Right, the distance to E will become 5, and E's parent will become F. And what about AE3? So this is a situation where, let's say distance to A is 0, the distance to E is 5, so no infinities involved here. A plus 3 is, well, the 5 is greater than 0 plus 3. So we're going to do the update. So what's going to change is the row for E, and we just found a better way. A better way, instead of going via F, we go directly from A, and the weight goes down. Okay, so that's update. It's important to understand update because all the algorithms we're going to look at use it. So any questions I could answer about update? Now, there is a perfect order of update operations. It turns out that if you know the solution ahead of time, and I've indicated the solution in yellow, I'll let you maybe think about it. If someone just told you, by the way, over here are the yellow edges that make up the shortest path tree, what would be the optimal perfect order in which to update the edges so that you don't waste any time? You don't do any updates that have no effect. You don't have any updates that later get updated again. You know that you always go, every update gives you the shortest path to some vertex. What update would you do first? Would you update that edge from D to H because it's yellow? Yeah?
You would start with A to B.
Right. I do that edge from A to B. And that would set the distance to B to be 2, which we know is the answer. And its parent to A, which we know to be the answer. Okay? What would you update next?
B to C.
B to C. That would set the distance to C to be 3, which is known to be the answer, and its parent to be B. What would you do next? Either C to G or C to D would work. Do you see the idea? You sort of do the edges as they fan out from A. I mean, this isn't realistic. We don't know the solution. We're trying to find the solution. But this is saying that if you knew the solution, you could do it just with these 1, 2, 3, 4, 5, 6, 7, in general, at most V minus 1 update operations. Okay? Now, what would happen if you updated A to B, and then you did a bunch of random updates? And then you updated F to C, and did a bunch of random updates. And then you updated C to D, and did a bunch of random updates. So in other words, you had a bunch of random updates, but sprinkled through were the those yellow updates in the proper order.
You'd get the right answer eventually?
Right, you get the right answer originally, because remember I told you, it's no harm to do things at random. It's no guarantee you'll converge, that you'll finish, but it does no harm. So you can choose any order of updates you want, as long as the updates include updates of those yellow edges in the right order, you're going to get the answer in the end. And all these algorithms guarantee that whatever updates they do, the yellow updates are done at some point and they're done in the right order. And that's why they all work. So, this is what we just talked about. So we need to update the edge leading into a vertex before we update the ones leaving. That's the fundamental thing. So if you know the yellow edges and you follow this rule, update them in the proper order, you'll have the answer. And then you can take that optimal update, throw any random updates into that list you want in any order, and you still got a solution. You're just wasting time. So, what will be the ultimate brute force algorithm that's guaranteed? We're not going to think very hard. We're going to be guaranteed that we get an answer, get the right answer. Yeah.
Go through every path possible and then find the minimum one.
More brute force than that. Yeah.
Try every edge in every order.
Well, he said try every edge, update every edge in every order.
So like,
Okay. Finding every order is hard. But something simpler than that, I guess. Yeah.
Just update every edge.
Update every edge. Just doesn't matter what order, just update them all. Now, when you're done updating them all, what do you know? Are you done? Yeah?
The distance to A's children.
The distance to what?
A's children.
Okay, so in other words, if you update them all, you're guaranteed to have updated A to B, right? So after the first pass of updating all the edges, we know that the yellow edges that lead out of A have all been updated. In this case, they're just one. So update them all again. What does that guarantee about this graph? Now we've done B to C, and furthermore, we know that there was an update of A to B in the first pass that came before the update to B to C in the second pass. Now there may be other updates of A to B and B to C that happened. Maybe the first pass you did B, C to no effect and then A, B. In the second pass, you did them in the other order. But that's okay. A to B is guaranteed to have happened in the first pass. B to C is guaranteed to be happening in the second pass after A to B. Okay? Do it again. This time you've dealt with the edge from C to G and C to D. Both of those will be updated in the third pass, in addition to having been done in the first two passes. So you just keep doing this. How long do you have to do it before you're guaranteed that whatever updates have happened, there's a subsequence that are the yellow edges in the right order? What's the most updates you have to do? In other words, what's the most number of edges that could occur in one of these short paths? Yeah.
I imagine it's equal to the distance of a unweighted breadth first search. Like.
Okay, so what's the longest path in a breadth first search? In a graph with V vertices. It's V minus 1 actually, not V. Imagine a situation where you had to, the shortest path tree was just a linked list basically. The yellow edges formed a linked list. That could be at least length V minus, at most V minus 1 edges. So the brute force solution is just V minus 1 times, update every edge. Update every edge, do it again, V minus 1 times. That's guaranteed to waste a lot of time, but also update the yellow edges in the proper order at some point. And you're done. So that is called, well, I guess I meant to show you this first. This is an animation of updating the edges in the right order. So we update that edge from A to B, and then B to C, and then C to D, and so on. So if you know the right order to update the edges in, that works out. If you don't, that's okay. Just do them all over and over again, and you'll get to this eventually. So that's called Bellman-Ford. So Bellman-Ford algorithm is very simple to understand. It's just a whole pile of updates. This is just making all the observations that I talked about before. You just update all the edges, do it again and again and again as a way of guaranteeing that the proper edges are updated in addition to everything else. So you just initialize the data structure like before, and in v minus 1 times, we update every edge. Very simple. So why you studied Dijkstra's algorithm in 2420? Why bother with Dijkstra's algorithm when you got Bellman-Ford? All Bellman-Ford assumes about the graph is no net negative cycles. It does not assume no negative edges, which Dijkstra's algorithm assumes. So why bother with Dijkstra's algorithm when this is more general? Yeah?
Is Dijkstra's more efficient?
Dijkstra's is more efficient. Yeah,
There are a lot of real-world situations that don't have negative edges.
that is true. There are lots of real-world, if you're trying to find the shortest distance between two cities, you're not going to get negative distances. Yeah. So, but there are situations where you're going to have negative edges, and this is sort of the most general one. This is the most general algorithm that will solve under the assumption that there's no net negative costs. So how inefficient is this thing? Yeah? Well, is it v squared? Well, let's think about it.
So is v squared 1 VMP?
Before we do that, here's an optimization. At most, you got to go v minus 1 times with this loop. Because the longest path, the longest path is a length v minus 1. You can stop early. What if you do an iteration and nothing changes? What if you do all the updates once and do them again, and that second time you notice that we never change anything in either array? None of the updates have an effect. Why can we stop right then? Yeah.
With another iteration won't change anything.
Right. If no update changed anything the first time, it's not going to change anything the next time either. So if you use that optimization, which is very cheap, you can stop potentially after 2 repetitions instead of having to do the full v minus 1. So in the worst case, you're going to have to do v minus 1. In the best case, you have to do 2. In reality, the number you have to do depends on how deep that yellow tree is. I should say, the number of repetitions you have to do in the worst case before things stop changing is going to depend on the depth of the yellow tree. You won't have to go to full v minus 1 if that yellow tree is shallow. Turns out you just have to go a few iterations, and things will stop changing. But in the absolute worst case, you're going to get v minus 1 repetitions. So let's analyze it. What's the cost of the initialization step, that first chunk of code? Setting up the distance in previous arrays. All right, that's just O of v, just like before. What's the body of the loop? So this for each loop with the update. The body of the repeat loop. Well, let's see. We're going to run the update operation e time. So what we're going to have to do here is identify all the edges and update them. So we're going to have to do the enumeration and update. And how many times does that loop run? V minus 1, which is O of v. So you end up with O of v for the initialization, O of v times enumeration for the body of the loop, plus O of ve. Okay? And that simplifies to O of v times the cost of enumeration. And if it's a matrix, that's O of v cubed. And if it's a list, that's O of v squared plus ve. So not linear. V cubed, which is actually pretty bad. So,
I mean, it's not.
an easy analysis.
It's polynomial.
It's polynomial, right? So, yeah, when we start talking about NP completeness, it'll look pretty
Yeah.
good. But from the standpoint of, v squared versus v cubed's a lot worse. So again, the analysis is straightforward because it's so simple. Because we're just, call that v. So the factor of v came from there. We're enumerating the edges and doing the updates. Now there are another optimization you can do. You can really don't have to enumerate the edges. You could, depending on what structure you're using, you can make small improvements by just making a list of all the edges once, and then dispensing with the matrix or the adjacency list. But in the worst case, it's going to be this anyway. Okay, so Bellman-Ford. Any questions I could answer about Bellman-Ford?
Yeah. Why doesn't it just why is it O of B E num, not just O of B E? Wouldn't O of B E be more of a bigger, I guess, threshold?
Okay, what you're asking.
Yeah. So in total, why is it?
So why is this bigger than that?
Yeah.
Okay. So just compare the cost of enumeration to E.
Okay.
The cost of enumerating all the edges is going to be at least as big as E, because it has to find all the edges.
Okay.
Plus there may be extra work it does in dealing with the zeros in the matrix. So this enumeration cost has to be at least as big as E. So that's why I just simplified it all over that. Yeah.
So because we consider it linear, if the matrix is O of B squared and the list is O of B
Plus E.
plus E, is this still considered cubic and quadratic respectively, or is it like?
Yeah, that's a reasonable question. Is this really cubic if we're willing to call a v squared algorithm linear? But I've never seen it. Yeah, I don't have a special term for it. But yeah, it's a factor of v worse than the linear algorithm's been looking at. And remember that linear, calling of the algorithms we looked at linear is only when you're looking at the size of the data structure as opposed to the size of the graph, which can be different. All right, so we're going to end up looking at Dijkstra's algorithm, which you've seen before, which is another special case. Dijkstra's algorithm allows no negative edges at all. And we got this at another extreme. Can you think of one other special case?
Only negative edges.
Only negative edges. Well, besides that. Yeah.
We have an obstacle?
No, not we have an obstacle. Yeah.
No cycles? It's
No,
DAG?
no cycles, a DAG, right. So what we'll start with next time is we'll see how can we do better if we know if the graph is a DAG. Because there are no cycles to worry about. And then Dijkstra's algorithm allows cycles but no negative edges. So with the DAG, no cycles, the edges can be negative. With Dijkstra's, no negative edges.
So the NP complete version of this, that has it allows like negative
Anything.
cycles, right?
It allows negative cycles, but you can't use them. You have to detect them. All right, we'll see you next time.